Hi, everybody. In today's lecture, I'd like to talk to you about capacitance and capacitors. So let me get started. I'll share my screen. So capacitance, here we go. And this is in chapter 3 in Purcell and Morin, and I'll also provide you with some appropriate links to where it is in our supplemental text, Chavez and Sherwood. So capacitors are devices that store charge and energy. And capacitors can be found all over the place. Radio receivers, filters and power supplies. They help eliminate sparking in automobile ignition systems. And they're also energy storing devices and electronic flashes. And here's a little camera that's been broken down here in this picture. And you can see there's a big capacitor right there, and that's to power the flash. So capacitors can also be found in some important medical devices like defibrillators. So for example, if you get a heart rhythm that's either stopped or gotten out of rhythm, then what can happen is they can start a normal rhythm again by applying a really strong electric charge, give you a jolt of electric energy, and that helps put you in your normal beat pattern. And so they have very large capacitors in these defibrillators that do that job for you. Now, in general, capacitors can act as energy reservoirs, and those energy reservoirs can be charged and then discharged quickly if needed to provide large amounts of energy in a short pulse. But they can also, if you're using them in these filters and power supplies, or in a power supply like, for example, one of those universal power supplies, when you lose power in your home and you need the power to run for a brief amount of time so that you can shut down your computer or whatever else you're doing, then those can be, depending on the load that you hooked up to, used to power for a decent length of time. Now we're going to use the equation to define the capacitance. The capacitance symbol that we'll use is a capital C. And the capacitance C of a capacitor is the ratio of the charge stored on one of the plates of the conductor to the potential difference or voltage between those conductors. So C is equal to Q over delta V. And I'll get a little bit more specific about each one of those variables in turn here in a second. But for now, we're familiar with charge. The SI unit of that is the coulomb. And the SI unit of voltage is, of course, the volt. Potential difference is the volt. And so the SI unit of capacitance is named in honor of Michael Faraday, and it's the farad, and it's a coulomb per volt. So 1 farad is 1 coulomb per volt. Now, farad is actually a really large unit of capacitance, and so most of the capacitors that you'll find if you do some electronics courses are usually microfarads, nanofarads, picofarads, things like that. Now, we can find the capacitance for an object. The capacitance for an object, as we'll see, will be dependent upon the object's geometry for the most part. So to show you this, let's talk about the capacitance for an isolated sphere. And we're going to assume that we have a charged spherical conductor and it has a radius A. Now let's assume that that sphere will have the same capacitance as if it would if it were a sphere of infinite radius that were concentric with the original sphere. So basically what we're going to do is we're going to use this equation for capacitance. C is equal to Q over delta V. And what we're going to do is reference the delta V, the voltage, with respect to the 2 points of interest, which would be the voltage at the surface of the sphere, and then the voltage infinitely far away from that sphere's surface. And so if the sphere has a charge Q and radius A, then doing C is equal to Q over delta V would give us Q on top. And then on the bottom, the voltage at the surface of the sphere as reference to infinity, which we've shown in previous lectures, is the Coulomb constant K times Q over A, where A is the radius and Q is the charge. Now you can see here that the Q's cancel out top and bottom. And so that leaves us with A over K, the Coulomb constant. And of course, the Coulomb constant K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. And so that means that for an isolated sphere, the capacitance would be equal to 4 pi epsilon naught A. Okay? So you can see here that the capacitance is dependent only upon the geometry and some constants, including epsilon naught. Now, that's for an isolated sphere, and it's true that there can be different capacitances for either a single object or more than 2 objects. But the typical kind of capacitor that you'll find in a circuit, most commercial capacitors, in other words, consist of 2 conductors. And we call those conductors plates. And what happens is we put the capacitor in a circuit, usually hook it up to some kind of voltage source, and then the capacitor plates charge. The charge on the two plates will be equal in magnitude, but opposite in sign. So one plate, for example, will carry a charge of plus Q, and the other one will carry a charge of minus Q. And that's what happens with, typical capacitors that you find in circuits and commercially available products. So because they are equally and oppositely charged, plus Q and minus Q, then there's going to be a voltage difference in between those two plates, plus Q and minus Q. And that's, of course, because there's an electric field, as shown here by these electric field lines in orange, that points from the positive to the negative plate. And anytime you have a field, you also have a voltage. Okay. Now, the capacitance, since it's going to depend upon the geometry, will always be a positive quantity. Once you set a capacitor up and fix its geometry and give it a whatever dielectric that you're going to give, more on that later, the capacitance will stay the same. Okay, so the capacitance for any given capacitor is a constant that just depends on the geometry and the configuration. This capacitance is going to be a measure of that capacitor's ability to store charge. And as we said, for most commercial capacitors, you'll have microfarads for picofarads because the farad is a really large unit. Now, the parallel plate capacitor isn't one that is typically hugely used in commercial applications, but it is a really nice capacitor to look at when we want to think about what the capacitance is and kind of visualize things because it's quite simple, okay? So let's focus in on the parallel plate capacitor for a little bit so we can develop that conceptual understanding. Let's say that we have a parallel plate capacitor and it's separated just by a vacuum, okay, or air in between the plates. And you have a charge of plus Q on one and a charge of minus Q on the other plate because it's been hooked up to a battery and it's been that way for a while. The area of each of the plates is A, we'll call it big A, and the separation in between the plates of the capacitor is little d. Now, when we first hook this capacitor up to a battery, as is shown here, the battery has a positive terminal and a negative terminal, okay? So the positive terminal is the higher voltage side, and the negative terminal we usually refer to as ground and reference it as having a 0 voltage, okay? So what happens is we're going to use this battery and establish an electric field in the circuit. Okay, so in this case, you know that electric fields point away from the positive and towards the negative terminal. And so we're going to have an electric field that kind of flows counterclockwise through our little circular circuit here. Okay, I'm sorry, clockwise. Did I say counterclockwise? The electric field goes clockwise. Okay, now this electric field that's established in our circuit, it's going to apply a force on the electrons in the wire. Okay, so of course, in conductors, you have these free electrons. And here we have this electric field that's moving clockwise. And so what that means is that the electrons, they want to move upstream of an electric field. So the electrons would want to move counterclockwise, okay? Now, in between the capacitor plates, there's no connecting wires or anything like that. The plates aren't touching. And so what happens is you've got this counterclockwise motion of the electrons in the circuit. And that means that electrons are going to want to leave the negative terminal of that battery and travel onto this right-hand side plate. And that allows the right-hand side plate to eventually build up a negative charge, as indicated here by minus Q, okay? Now, likewise, the electrons on the other side, okay, they're still going to want to flow counterclockwise, and that means they're going to flow towards the positive terminal of the battery, away from this plate. And that leaves a positive charge plus Q on the left-hand side plate, right? Now, this flow of electrons will continue until the voltage in between the capacitor plates equals, in magnitude, the voltage at the battery terminals, okay? Now, it's equal in magnitude, but of course it's going to be opposite in direction because you're going to have, it's equal in magnitude, but the voltage drop is going to drop across the capacitor plates. So the voltage supplied by the battery then gets dropped across those capacitor plates so that as you walk around your circuit, your total net voltage, when you come back to your beginning spot, your total net change in voltage is 0. In other words, you're going to start here at the positive terminal, a certain voltage. You're going to walk all the way around. And then when you come back, you better end up at the same voltage, right? So whatever positive voltage you're given here drops across the capacitor plates and comes back. Now that voltage across the plates, as I said, is going to equal in magnitude towards the voltage between the battery terminals. Okay, now once that voltage is achieved between the capacitor plates that equals the magnitude of the voltage across the battery, then that is going to be equilibrium. And that will mean that no current will continue to flow in the circuit and it'll stop and you'll have a net static charge on your capacitor plates. Okay. Now, once that happens, you're going to have a positively charged plate and a negatively charged plate. So let's take a look, remembering our Gauss's law, at what's happening at that positively charged plate. So you have basically, in Gauss's law, you can assume that your plate is large compared to the separation between the plates. And so that means that you can consider it to approximately an infinitely large plate, okay? So we're gonna draw our Gaussian surface here. We have a Gaussian pillbox, and the net electric flux here will equal to the enclosed charge divided by epsilon naught. So remember, Gauss's law says that net electric flux is equal to the integral about the enclosed surface of E dot dA, which is equal to Q enclosed over epsilon naught. Now here, the dot product of the electric field and the area vector is only going to give you a non-zero value here at the end caps, as you can see, okay? Everywhere else, the electric field would point perpendicular to the area vector for the surface. So it's only the end caps that contribute. Now you have two end caps, okay? And the electric field points away from the positive plate on either side. And so on the left-hand side with our integral of E dot dA, we end up with 2 times the magnitude of the electric field times the area of that's enclosed by the end caps of our Gaussian surface. Now that's going to equal to, on the right-hand side of our Gauss's law, Q enclosed divided by epsilon naught. And Q enclosed will be our surface charge density on the plate, or the charge per unit area sigma, times the area of the end cap. So that's going to be Q enclosed is sigma A. And then that's divided by epsilon naught, because Gauss's law says the flux is Q over epsilon naught. So now we can cancel out the A on both sides of our equation and solve for the electric field. And we can see that the electric field due to the positive plate is sigma over 2 epsilon naught. Okay, so if you want a more detailed explanation of this, you can go back to the Gauss's law lectures. Now, of course, there's two plates. There's the positive plate and the negative plate. The electric field is going to point away from the positive plate with sigma over 2 epsilon naught, and it's going to point towards the negative plate. And that's again with a magnitude of sigma over 2 epsilon naught. So that means that the net field in between the plates of the capacitor is sigma over epsilon naught. So we have this between the plates of capacitor, relatively uniform, straight electric field that points, in this case, to the right, okay? And that field there is sigma over epsilon naught, which is the charge over the area, Q over A, divided by epsilon naught. Now, we can plug into our formula, C is equal to Q over delta V, and solve for the capacitance for a parallel plate capacitor. So to do this, let's first solve for the voltage in between the plates of a parallel plate capacitor. Okay, so that's shown here. We're going to do delta V is equal to the negative line integral of E dot ds. That's our general relationship that is between voltage and electric field. So now in this case, we have a uniform electric field E, right? And that E is sigma over epsilon naught, and it points straight to the right. And so if we want the voltage between the plates, what we would do is walk along the electric field lines from the left-hand plate to the right-hand plate, which are separated by D. So that's actually a very straightforward integral. E is a constant. Our electric field is a constant, so I can bring it outside. And the dot product just gives us cosine of 0, which is 1. So that goes away. And so we just end up with the integral of our negative E times the integral of ds. And when we evaluate ds, the path length there is d. So we just get minus ed. Now we only care about the magnitude of this potential difference because, you know, C is equal to Q over delta V is always going to give us a positive number. Capacitance is always positive. So we take that absolute value. Okay. And then we can plug into our formula for capacitance. So we have C is equal to Q over delta V, which is Q over ED. Okay. And now that would be Q over A epsilon naught times D, right? So that's here shown here in the denominator, right? So here E times D would be QD over A epsilon naught, and that's what we're plugging in the bottom there for delta V. The Q's cancel out, and then we're left out with the capacitance for a parallel plate capacitor, which is epsilon naught A over D. So yet again, just like our isolated sphere, we can see that our capacitance is something that depends only on the geometry of the situation in this case, and some constants epsilon naught. One more example of how to find the capacitance for a different geometry, and this is capacitance of a spherical capacitor as shown here. And so what we've got in this case is two nested spheres that share a common origin. The inner sphere has charge plus Q on it, and the outer spherical shell has charge minus Q. And in between, of course, there's a vacuum. And our spherical shells have radius A and B. Okay, so that's the idea there. Now, we know what the voltage is, or what the electric field is, I'm sorry, for a spherical shell when we're outside of that spherical shell. Yet again, this is something that we covered when we discussed Gauss's law. So I'm not going to belabor this point too much. You should look back at that Gauss's law explanation. But the electric field for a spherical shell just outside the shell is kq over r squared. K is the Coulomb constant, q is the charge, and r is the distance from the center of the spherical shell to the point in question. Now, this electric field points radially outward, and so we would have the electric field of kq over r squared r hat. Now, if we want the voltage difference in between the inner sphere and the outer sphere, then we would be walking from the surface of sphere, I'll call it A, to the surface of sphere B. And that would be in the radial direction. So our dl here would be dr r hat. Now, yet again, in this case, our path, dr r hat, and our electric field, also pointing in the r hat, are parallel to one another. So that dot product gives us a cosine of 0, which gives us the 1, okay? And then we're just integrating negative kq over r squared dr, and we're integrating that from A to B. So when we integrate 1 over r squared, the kq part's a constant, so we can pull it outside of the integral. When we integrate 1 over r squared, we get negative 1 over r. So that cancels out with the minus sign out front and the negative sign from the negative 1 over r, and we end up with a positive value. And then we evaluate that 1 over r from A to B. So we end up with a voltage difference of kq times 1 over B minus 1 over A for our voltage, okay? And now we're going to take that voltage and we're going to plug it into our formula for the capacitance. C is equal to Q over delta V. And then I have Q over KQ times 1 over B minus 1 over A. The Q's cancel out top and bottom, and I end up with forming a common denominator for 1 over B minus 1 over A. It would be 1 over K times A minus B divided by AB. And then I move the AB to the numerator, and I have AB over K times A minus B. And that would be the capacitance for a spherical capacitor. So to sum this up, if you're asked to find the capacitance for some sort of object of random geometry, what you would do is you would first find that potential difference between the plates. Now, typically, you'll be given problems that have a high degree of symmetry. And so what you should probably do most of the time is use Gauss's law to solve for the electric field, and then use the relationship in between the voltage and the electric field, delta V is equal to the negative integral of E dot ds, and use that to solve for the voltage, okay? And then you plug that voltage into your capacitance relationship, C is equal to Q over delta V, and you should see that things cancel out, okay? And you're only left with quantities that depend upon constants in your geometry. All right, so now let's talk about how we store energy in capacitors. So let's take another look again at our simple little circuit that just has a battery and a parallel plate capacitor and a switch, okay? And this is our system, and it's a circuit, right? Now, if we have that switch initially open, then all of the energy in the system, we're going to say that our capacitor is initially uncharged. All of the energy in the system is the chemical energy in the battery, right? Then you close the switch and the energy is transformed from chemical to electric potential energy. In other words, a field's established, right? An electric field's established in the wire, and that causes the electrons to move away from the positive plate and towards that negative plate. And you get that charge buildup on the capacitor plates. Now, because these charges are separated from one another, you get the establishment of that electric field. And electric fields store potential energy, right? Electric fields are energy storage places, okay? And so that's how the chemical is transformed into electric potential energy in the form of the electric field between the capacitor plates. So let's figure out how we're going to write an expression for how much potential energy can be stored in the capacitor. Now let's remember that the magnitude of the work done is going to equal to the magnitude of the potential energy. So let's imagine what we're going to do is do some work by transferring a charge from one plate to another by walking around our circuit, right? And remember that your potential energy and your electric potential or voltage is related to one another via the potential energy is equal to Q times the voltage, where Q is the charge. And so if we're going to write that down, then I could write that the little differential of the work needed to move around would be my voltage, delta V, times my little dq of charge that I'm moving. Now, using my relationship for capacitance, C is equal to Q over delta V, I can sub in for what delta V is, and I would write Q over C. So then I would have my little differential amount of work would be Q over C times dq. Now, if I want to integrate that up to a total charge big Q stored in the capacitor, then my little d work would be, would get integrated to give me the work, and that would be the integral from 0 to big Q of Q over C dq. Now, 1 over C would pull out up front as a constant, and when you integrate little q dq, you get 1/2 Q squared. And then evaluated from 0 to big Q, you'd end up with big Q squared over 2C. And that would be the total work required to transfer amount of charge big Q from one plate to the other plate in our simplified little circuit that we showed here a second ago, okay? Now, using our relationship in terms of C is equal to Q over delta V, I can plug into that equation that we have for our net work done, which equals magnitude of potential energy stored U, and then rearrange my energy storage formula to be in terms of any two of the three variables in C is equal to Q over delta V. So since Q squared over 2C is one of them, I could sub in C is equal to Q over delta V there on the bottom, right? And then I would end up with an expression for the potential energy of 1/2 Q delta V, right? Or I could sub in into that one, right? Q would be equal to C times Z, and then that would give me 1/2 C delta V squared. And so any one of these three expressions is fine for finding the potential energy stored in a capacitor. Right? So you can see, looking at this equation, that the energy stored increases as the charge increases and as the potential difference increases. And in practice, there's going to be a voltage and max voltage before the discharge occurs between the plates. And that's known as the dielectric breakdown. And we'll talk more about that when we talk about dielectrics. So we have our equations for potential energy stored, and that energy is stored in the electric field. So for a parallel plate capacitor, let's just take a look at that a second. What we would have is 1/2 C delta V squared. Plugging in for the value of C would be epsilon naught A over D. So we have 1/2 epsilon naught A over D times, and then the voltage there can be written for a parallel plate capacitor as the electric field times the distance between the plates D. So that would give us then 1/2 epsilon naught AD times E squared once we simplified everything out, okay? Now, what this tells us is that since A times D is equal to the volume in between the plates of our parallel plate capacitor, remember that for any rectangular solid, the area of the base times the height, right, is your volume. So that's basically what we've got going on here with our A times D. Then what we're saying here is that potential energy stored would be 1/2 epsilon naught times E squared, where E is the electric field magnitude, times that volume, okay? Now, you might remember that in a previous lecture, we discussed the concept of energy density, which we called little u sub E, okay? And we said that the energy density is the energy per unit volume, in this case, that's stored in the electric field, And so our energy density equation is coming back to us here, even though we kind of did a little back derivation for it for between between the plates of a parallel plate capacitor. This is a generally true statement. And there's energy stored in all electric fields, and the energy density stored in an electric field is 1/2 epsilon naught times the magnitude of that field squared. Okay. All right. I hope that you understood that, and I hope it was relatively straightforward. And as always, I'll see you